Let's have a look at the concept of the inverse of a matrix, and later we'll have a look at the determinant of a matrix. So let's start by filling in some blanks here. A square matrix has the same number of columns and rows. So for example, a 2 rows and 2 columns, or a 3 rows and 3 columns, these are examples of square matrices. And a particular kind of square matrix is known as an identity matrix. And an identity matrix has got 1s on its main diagonal and 0s everywhere else. Let me show you what I mean in this example. We have to write the 2 by 2 identity matrix. And so obviously it's going to have 2 rows and 2 columns. The 1s must be on the main diagonal. The main diagonal is always this one, from top left to bottom right. So those must be 1s, and I must have 0s everywhere else. There we go. And we can call this I, capital I, because we always use capital letters for matrices. But it might be a little bit more specific, even, to say I2, to show that this is the 2 by 2 identity matrix, not any other identity matrix. And a 3 by 3 identity matrix would be I or I3 if you want to really be specific. And we got a 3 by 3, 1s down the main diagonal and 0s everywhere else. Now the product of a real number, k, and 1 is of course just the same number k. Right? This is one of these properties you learned a long time ago, and we call this special number 1 the multiplicative identity. So here's this word identity again, meaning that an identity means that it keeps the identity of any number intact. So if we multiply any number by 1, the number itself has not changed. 1 has preserved its identity. Well, we can do this with matrices as well. The product of a square matrix A and an identity matrix I, well, the identity matrix should not change the identity of the matrix A, so we'll still get matrix A as our answer. So suppose that we've got A, a square by square, n by n square matrix. Then we can multiply that matrix, that n by n A matrix, by the identity, and we'll still get A. And we can take the identity, I've written a little I sub n to show that it's the identity matrix with those dimensions times the matrix A, and of course the identity doesn't change the value of A, we still have A as the answer. So let's actually practice this. We'll find the product of A, B, C, D and 1, 0, 0, 1. And of course, if you recognize this as the identity matrix, you can probably already anticipate that the answer will be this matrix unchanged. But let's actually work it out with some matrix multiplication. So A, B, C, D multiplied by 1, 0, 0, 1. Of course, these are compatible matrices for multiplication, because this one is a 2 by 2, and this one is a 2 by 2. The inner dimensions are the same, and so it is possible to multiply, and our resulting matrix will have the outer dimensions. It will become a 2 by 2 matrix itself. So, alright, here we go. So first row, first entry, A times 1 plus B times 0, that's just A. First row, second column, so that's A times 0 plus B times 1. Second row, first column, C times 1 plus D times 0. And lastly, second row, second column, so our second row times the second column is C times 0 plus D times 1. And just as we anticipated, we do get our original matrix of A, B, C, D, demonstrating that if we multiply a square matrix by an identity matrix, we will still end up with that same original square matrix. Now let's take it back to normal numbers for a moment and remind you that if you multiply some real number k by its reciprocal 1 over k, what are you going to get? Of course, they cancel out effectively, and you end up getting 1, the identity. And so 1 over k is known as the multiplicative inverse of k. K and 1 over k are inverses of one another, because when we multiply them, we get the identity. So moving back to matrices, if we could multiply some square matrix A by its inverse matrix, which is denoted as A with a little -1, please note that A with a little -1, it's not an exponent. This is not an exponent. It's not equal to 1 over A to the 1 or anything like that. You're probably going to find now, as you move on into more complicated mathematics, that in most situations, this -1 superscript up in the air usually will refer to the inverse of something. We'll use it for the inverse of a function. We'll use it for the inverse of a matrix. We'll use it for the inverse of trigonometric things. And so you might want to start getting accustomed. It's just an issue of context. And this is a situation where you have to interpret that the context of this superscript is not an exponent, it's an inverse. And that's always going to be the case with matrices. That little -1 will always be an inverse. So if we multiply an A by its A inverse, much like we did with the K's, you should get the identity, which we know is the matrix I. So if A is an n by n square matrix, then A times its inverse should give you the identity. And the inverse times A should give you the identity as well. In fact, A and A inverses are inverses of one another. So the inverse of A inverse is simply A. Okay, so let's suppose A is an n by n square matrix, and there exists some other n by n square matrix called B, such that if we multiplied them, we got I. The only way this can ever happen, the only way we can ever get the identity by multiplying two matrices, is if they are inverses of one another. It's important to note here that the inverse of a matrix only exists if the matrix is square. And there's two conditions to ensure that the inverse of a matrix exists. First one, the matrix must be square, and second, the determinant is not equal to 0. We'll talk about determinants later. So let's have a look at matrix A and B here. They're both square matrices with the same dimensions. We need to show that they are inverses of one another. Well, one way we can do this is to demonstrate that their product gives us the identity. So let's give this a try. We'll multiply A times B, and if we get the identity, we have proven them to be inverses of one another. So there's matrix A times matrix B. So we get 10 minus 9, -6 plus 6, 15 minus 15, and -9 plus 10. Simplifying, that gives me 1, 0, 0, 1. Great! Because we got the identity matrix, then we can establish A and B are inverses of one another. Now, I used to make my students years ago also multiply B times A to ensure that there they also got the identity matrix I. But I've never ever, I mean, there's no such situation where A times B could give you I, but then B times A gives you something different. That's simply impossible. It can't occur. And as a result, I no longer make students do the second check. As long as you've checked one of these and you got the identity matrix, that must mean that they are inverses of one another. And so we could state, for example, then, that B is equal to A inverse. Or we could say that A is equal to B inverse. They are inverses of one another. Now, and it's possible to actually calculate what the inverse of a matrix is without, I mean, in the example we just did, we were given the two matrices, and it turned out that we discovered they were inverses of one another. But what if you're only given one matrix? How would you find the inverse of it? Well, we end up having a nice formula for 2 by 2 situations. A 2 by 2 matrix A, B, C, D, its inverse will be 1 over AD minus BC, and you're going to see this thing later on, this denominator. This is known as the determinant. So 1 over the determinant. Anyway, for now, AD minus BC, 1 over that amount, and now we'll switch the A and the D around in the inverse. The D and the A are backwards, and the negative B and the negative C, B and C have just become the opposites of what they were. They stayed in the same place, but we stuck a negative sign in front of them. Let's practice this in example D. I've given you matrix A, this 2 by 2 matrix. We need to find A inverse. So we know that A inverse is going to equal 1 over the determinant, negative 4 times negative 3, minus 5 times 2. And now I've got, I have to switch the order of A and D. And these two stay where they are, but we stick negatives in front of them. 12 minus 10 is 2, so really I've got 1/2 in front. And that 1/2 is a scalar, which is applying to every single entry in the matrix. So I've got 1/2 of negative 3. I've got 1/2 of negative 5. I've got 1/2 of negative 2. And I've got 1/2 of negative 4. And that is the inverse to your matrix A. Now then, let's just prove this to you. Let's multiply A times this thing that we believe to be A inverse and verify that we do indeed get the identity matrix. And so I've got A, negative 4, 2, 5, negative 3. And I've got A inverse, negative 3 halves, negative 5 halves, negative 1, negative 2. You don't actually have to perform this check unless you've got extra time at the end of a quiz or test and kind of want to feel confident that you've got the correct answer. But I would finish every question before you do something like this. So negative 4 times negative 3 over 2 gives me positive 6. And plus 5 times negative 1 is plus negative 5. First row times second column, negative 4 times negative 5 over 2 gives 10. 5 times negative 2 gives me negative 10. Second row, first column, 2 times negative 3 over 2 is negative 3. Negative 3 times negative 3 is positive 3. And second row, second column, 2 times negative 5 over 2 is negative 5. And negative 3 times negative 2 is 6. And as you can see, we do get 1, 0, 0, 1, the identity, which proves that that this matrix is indeed the inverse of matrix A. We can also use the calculator to find inverses of square matrices. If we've got a 2 by 2 square matrix, well then I would expect you to know the formula and to be able to apply the formula to find the 2 by 2 inverse manually. But you don't have to find inverses of larger square matrices. It's just too difficult. And so let's use the calculator to do this. I'm going to create a matrix on the calculator by pressing second and coming to here, the x negative 1, and I get into the matrix. And I'm going to go over and I'm going to edit a matrix called A. So I select A, edit A, and I want this to be a 3 by 3 matrix. Now let's put in the entries. I've got 2, negative 1, 1. I've got negative 1, 3, 4. And I've got negative 2, 1, 0. Make sure you press enter after the last entry so that they have all been saved. Alright, I'm going to quit, so second mode to quit. And now I'm going to call up this matrix named A. So let's go back into the matrix menu, x negative 1. And this is why I'm going to the names column, not the edit column. The matrix named A, it's already selected, enter. There it is, matrix A. And I want to find the inverse of it. So here's the x to the negative 1 button. It's the same one we were using for matrix, but I just won't press second function first. There's my inverse. Hit enter. And there's our inverse. And so just thanks to the calculator, we can immediately conclude that A inverse is equal to negative 0.8, 0.2, negative 1.4, 1.6, 0.4, negative 1.8, and 1, 0, 1. And you could confirm this actually by taking that answer. So let's take, whoops, sorry, how do I do this? Second answer, there we go. And I don't want to add, actually, I want to multiply it by our matrix named A. Second matrix named A, and let's see what I get. Hooray! The identity matrix, which proves that, of course, A is the actual inverse.